Alright, so we're back. Here's question number 12. So here assignment 2-3. Oh, this one's a long one. So let me write it here. F at x equals 2x minus 1 squared. X plus 2, x plus 3 squared, x minus 3 cubed, x plus 2, x plus 3. All right, let's see what we got here. Just break it down one step at a time. So first thing I'm going to look is the domain, what x can't be, by looking at the denominator. So positive 3, negative 2, and negative 3. And then I'm going to reduce it down. So then what does f at x equal if I reduce it down? So we still have 2x minus 1 squared. Nothing reduces down. How about x subtract 3? No. X subtract 3 cubed. Nothing simplifies it down. X plus 2, that one is removable. So that means at negative 2 we have a hole. So I'm going to write that down. Negative 2, there's a hole. Also, notice x plus 3 makes x plus 3 squared just an x plus 3. So there's no longer x plus 3 in the denominator. It's removable. So the negative 3 got removed from the bottom. So there's a second hole at negative 3. Now, to figure out the y coordinate of it, you're going to plug it into here and then solve it. So if you plug negative 2, you get negative 5. Let me do that over here. You get negative 5 squared. Negative 2 plus 3 is 1. And then negative 2 and negative 3 is negative 5 cubed. So I'm going to reduce this down using a little bit of exponential understanding. Notice here we have the same base. So when you subtract, you really just have 1 over negative 5 left over. So the 2 subtract 3 leaves me with 1 negative 5 in the denominator. So it's negative 2 and negative 1/5. For the other one, which is at negative 3, where's that hole? So plug that in. That's negative 6 subtract 1, so that's negative 7 squared. Negative 3 plus 3, oh, that's helpful. That's 0. So because of that, 0 times divided by this other hole is at negative 3, 0, which leaves the vertical asymptote at x equals 3, and it has an odd exponent. So this is an odd asymptote. So we already have a lot of information. The x-intercepts here, look what's left in the numerator. 2x subtract 1. If I take 2x subtract 1 and make it equal to 0, add 1 and divide by 2, the 0 that comes from that is 1/2, and it has an even exponent. So that means it's going to touch there. Now this one, negative 3, is a hole. So the only x-intercept is there. The y-intercept is when I plug in 0. And if I plug in 0, I get 1 times 3, and it's 3 over negative 27, or negative 1/9 is the y-intercept. All right, so we're going to just sketch it to the best of our abilities. So what do I know so far? At negative 3, 0. Oh, and I got to look at the horizontal or end behavior of this too. I'll do that in a second. So if I was going to look at the power terms to know the end behavior, I have 2x squared. That's 4x squared when I expand it, the power term, times x. And then I have x cubed on the bottom. So if I put this all together, these divide out, and all that leaves me with is 4 for the horizontal asymptote, or the end behavior. So y equals 4, 1, 2, 3, 4. That's the horizontal. I have a vertical at 3. I have x-intercept at 1/2. I have a hole at -3 and 0. I have another hole at -2 and -1/5. Just estimate where that is. I have a y-intercept at -1/9. That's here. Down a little bit here, somewhere here. -1/9 is not as low as -1/5. So yeah, like here. Then I just need to understand what direction this is going. I know the end behavior is going to 4. So when I plug in a number that's bigger than +3, what's happening here? So a number bigger than +3 will give me positive answers everywhere. That means here it's going to infinity, and down here it's going to -infinity. It's an odd asymptote. So positive infinity, negative infinity. I know the end behavior is 4, so I know from here it's going to curve into 4. Here we got some loop-de-loops to worry about. So we have this. I know that there's a hole there, and that hole has an, there's a x-intercept. The holes are over here. The x-intercept has an even exponent. So with the even exponent, it's just going to touch and not cross. So I have this kind of behavior where it's going to touch. I have the y-intercept. I have this hole. I have this hole. So I'm going to connect them. Now, at this hole has an odd exponent. That's this one right here at -3. So I know it's going to cross over, and then I know the end behavior eventually is 4. And it may not go up that quickly to get to 4, but this is the overall picture, the sketch of it. So when I come here and I type it in, and it's going to be long to type in, 2x subtract 1 squared x plus 2, x plus 3 squared, and then the denominator has x subtract 3 cubed, x plus 2, and x plus 3. All right, I think I typed in right. So I want you to look at the graph. I'm going to zoom out just a little bit so you can see what's happening here. So notice on my graph, it does get to 4, and you can see it. So you can see the upper part. There's a horizontal asymptote at y equals 4. So the right and the left are going to 4. Here in the middle, you can see it's touching at 0.5, and then there's some holes here. So if I go across here at -3, there's a hole right there, and there's another hole at -2. So we have 2 holes like we have here. So in general, does this match the picture that I just did? Which it does. So again, I'm focused on the end behavior as well as the behavior at the asymptotes and holes and intercepts and putting the behavior all together. With calculus tools, we're going to do a much better job at graphing this. Right now we're just using pre-calculus tools to get a sketch of what we know. So it's good to have pre-calculus tools, then wait till we get calculus tools, and then it's going to be even more powerful. All right, number 13. Two more to graph. This one seems harmless, but we'll see if it is. Just 1 over root x. So I can tell you that the domain is all numbers greater than 0, or from 0 to infinity. So when I look at it, because any number, if I plug in 0 or anything less than 0, it's going to have a negative response. So it's going to act like an asymptote at 0. I know that there is no x or y intercept. So when I look at the numerator, there's no way that could be 0. If I plug in 0, it's undefined. So we have no intercepts So it'd be helpful to have some points that could help us along the way here. So I'm going to graph it, get a sense of what the behavior is. So first of all, I want you to notice that the square root of x in the denominator, what's going to happen is the square root of x is powerful enough to draw this to 0 as an n behavior. So as I plug in, there's nothing on the axes. If I plug in positive 1, the answer is positive 1. So at least you have a point to begin with, 1, 1. So what's happening when you plug in 1/2, 1/3, 1/4, when you look here, where is it going? And again, 0 is going to act like an asymptote. So I want you to notice that it's going to go to positive infinity from here. And then what's going to happen as it goes here to the right? What's the right end behavior? So the left end, it doesn't really have a left end. Right here at 0 it has behavior. But what's the right end? So as you put in 1,000, 1,000,000, 1,000,000,000, 1 over that, it's going to get closer and closer to 0. You'll never have an answer that's negative. It'll never be 0. So there's your curve of 1 over root x. So if we look here, can we confirm that's what 1 over root x looks like? Look at that. And it's even more here. Let's so you can see it. So you can see the general curve of it, and that it has a 0.11, which is helpful to have. But you can see how quickly it goes up to infinity and how to the right it's getting closer and closer to 0, but it will never be 0 as you zoom in. Perfect. Number 14. Last one to graph. I'm sure you're sad about that. So negative x over the square root of x squared subtract 1. I said, hey, that's the same as problem 3. So I'm going to go back to problem 3 and think, what did we already discover? I don't want to reinvent the wheel. So what we realized about the domain is that it goes from negative infinity to positive 1, not including that, and then, or to negative 1, and then from 1 to infinity. So there's a little gap between negative 1 and positive 1. We said there's a horizontal asymptote both at positive 1 and negative 1 when we graph this. So they're the things that we already discovered. When I look here, I can see that there's an x-intercept at 0, 0. So this gives me that. I can also tell you there's a y-intercept also at that. So let's use that. But saying that, 0, 0, that if I plug in 0, I get imaginary answer, so that's no good. There's actually no intercepts. So it would have been 0, 0, but that's not in my domain restriction. So let's see what's happening here. So because it's negative x, it's going to be a negative divided by a positive. Negative 1 is actually going to the right. Positive 1 is going to the left. So one asymptote is negative x over positive x, and the other is negative x over negative x. So this is the right end, and this is the left end. So negative x over positive x, that's what gives me negative 1. Negative x over negative x, that's what gives me positive 1. So you can get a sense of what's happening there. Now, this is only going to start after 1. So what's the picture going to look like? So there's going to be a gap in the middle. It'd be nice to have a point, right, to be able to go through, to be able to understand it. So it's not going to be 1 or 2, 3, 4, 5. I was trying to think of like what would be a nice point to understand the behavior of what's happening there. So again, think, where's it at negative 1 and positive 1? So think of like at negative 1 and at positive 1. There's nothing going to be here in the middle. And so what's going to happen is you plug in answers that are close to negative 1. What are going to happen to answers that are here? And so the behavior here is going to have this kind of a curve where this is the end behavior. And this is going to have this curve where this is the end behavior. So you can see the positive and going to infinity and negative infinity. It's a pretty challenging looking graph just to sketch without having a graphing calculator. So let's go to the graphing calculator, make sure that we're doing it okay. So we have negative x, and then we have the square root of x squared subtract 1. So this is the most challenging one to be able to sketch. I'll press the home button here. So when you look here, can you see that there is nothing between -1 and +1? And you can see the behavior of the curve. The end behavior, the right end behavior goes to -1, the left end behavior goes to +1, and then it goes to infinity and negative infinity in the middle, and trying to put the pieces together. So I know that was a challenge, but we got through it together. Number 15 and on are not graphing questions. So number 15 are just limit questions. So they're going to be a lot simpler. So let's do that together, and then we'll be done for this assignment. So the good thing about these assignments is that they're not just about the new lesson. There's always review questions embedded, so keep practicing so that what you forget. So we have the limit as x approaches 2 of 2 minus x over x squared subtract 4. So how are we going to evaluate a limit? So step 1 is to plug in 2. See, it's indeterminate. So we're going to see if we can factor out the whole to be able to evaluate the limit. So this is a difference of squares. I want you to notice that 2 subtract x and x subtract 2, they're almost the same. They're actually opposite factors, so when you divide them out, what you're left with is -1. But now we divided out that whole, so now you can substitute in 2. So the answer is -1/4. Number 16. 16 is looking off a graph. So I'm going to show you the graph, and can you look off a graph to evaluate a limit? So we have A, B, and C for number 16. So this is all as x is approaching 1. So we have one-sided limits, and then we have a two-sided limits. So as x approaches -1 from the left, what's the limit? So here's -1. So from the left, what's the limit? From the right, what's the limit? And then does the limit exist there? So you could see from the left, the answer is +1. From the right, the answer is 0. And then there, it doesn't even exist because there's a jump there. So there's no two-side limit. So again, from the left, the answer was +1. From the right, the y coordinate was 0. And then there's no two-side limit because there's a jump there. Number 17. What's the limit as x approaches 4? And this is the square root of x minus 2 over x minus 4 subtract 4. So I plug 4 in. It's indeterminate. I multiply times the conjugate to undo that whole. So I can't factor it. So that's the limit as x approaches 4. The numerator, root x times root x, and -2 times 2. The denominator, put them beside each other. Notice the whole will divide out. Now you can plug in. What you didn't see is there's a 1 there. And when you plug in, you get the answer 1/4. Number 18. You have the limit as x approaches 3, and you have the absolute value of x minus 3 over x subtract 3. Now, when you plug 3 in, it is indeterminate, so it could or may not exist. What does this graph look like? Well, if you plug in a number bigger than 3, you get +1. If you plug in any number smaller than 3, you get -1. And exactly at 3, there's a jump. So this limit does not exist because there's a jump that goes from -1 to 1 when x approaches 3. So it's the jump that means the limit does not exist. Number 19, we have a piecewise. So the limit as x approaches 1, you had x and x subtract 1. So this is valid when x is less than or equal to 1. This is valid when x is greater than 1. And so each piece is continuous, so the limit would exist. Now at 1, what's happening? So as it approaches 1, plug it in top and bottom. I want you to notice it does not exist because, again, there's a jump. Why is there a jump? So plug in 1, you get 1. Plug in 1, you get 0. So it's a jump from 1 to 0. So therefore, the limit doesn't exist. The left side does not agree with the right side. Number 20. The limit as x approaches 0, and the top piece is x squared subtract 5. It's valid when x is less than or equal to 0. 2x subtract 5. That's valid when x is greater than 0. And so what's happening at 0? So when you plug it into the top and plug it into the bottom, they both agree what the limit is. So both the top and bottom, it's approaching negative 5. So there is no jump there. It's a continuous function. 21. Oh, my favorite, the step functions. The limit as x approaches 1 of x divided by 4 plus 2. Now the good news is step 1 is plug it in. Well, when you plug it in, you get 1/4 plus 2. Well, 2 1/4 is not an integer. It only doesn't exist for a jump when the answer is an integer. 2 1/4 is not an integer. So that's your answer. It's 2 1/4. Oh, and actually, what is the greatest integer less than or equal to that? So because that is not an integer, it's in the middle of the step. And what's the greatest integer less than or equal to that? The answer is 2. So when you think of your step function, this point is in the middle of what makes a step. That's good. It's only the jumps that are bad. So that doesn't create a jump. It's in the middle of the step, so the limit exists. What's the y coordinate there? And the answer is 2. 22. The limit as x approaches 1, and again a step function, 4x plus 2. Now for this one, notice that when you plug in, you get an integer answer. So because you get an integer answer, there's a jump at 22. It's not in the middle of the step. It is the jump in the graph. And because it's the jump, it does not exist. 23. The limit as x approaches 2, and it's x over x minus 2. Step 1, plug in. Well, when I plug in, I get 2 over 0. That is not indeterminate. There's nothing to factor. There's nothing removable. So when it approaches 2, it's approaching the asymptote, and the limit does not exist at that asymptote. Done. So when you plug in, you get 2 over 0. That is not indeterminate. That's just undefined. It's non-removable. There's an asymptote, so the limit does not exist. 24. The limit as x approaches 2. Some of these you need to practice, right? Like just press pause, do the work, and then press play to see if you did it right, and enjoy that you did it correctly. The numerator I'm just going to factor, so I'm going to factor out an x. I want you to notice that x subtract 2 is removable. That if I plugged in 2, you would have indeterminate. But I remove the whole. Now I can plug in 2, and I have my answer. Try 25. Like, press pause. Just try it. Now press play. So the limit as x approaches 2 of x over x minus 2 squared. Now, step 1 is plug in. So if you substitute in, you get 2 over 0. That is undefined. It's an asymptote. You can always write down the answer is does not exist. But there's another answer it could be. So at 2, if you would look at the graph, that because it's squared, both sides are going in the same direction. So if I plug in a number bigger than 2, you know, like 3, or smaller than 2, like 1, both answers are positive. Both answers are going to positive infinity. So if you looked off the graph, you could also rightly say that the limit here is infinity because both sides are going in the same direction because of that too. But you could also say it doesn't exist because it's undefined. A limit at an asymptote, you can always say it does not exist. The limit as x approaches infinity. This is end behavior question. 3x squared subtract 5x, 7x squared plus 2. So what do I look at? This is the right end. That's the first thing I look at. So for the right end, what are the power terms that are involved? So on top, the most powerful term is 3x squared. On the bottom is 7x squared. That simplifies to just 3 over 7. And because it's a constant, the right and the left end both go to that number, 3 over 7. Done. So even if it said the left end, you'd still have the same answer. This is another way of understanding there's a horizontal asymptote. See, the horizontal asymptote is like a limit, and it gives you the end behavior. 27. The limit as x approaches 2 of x squared subtract 9. Wow, right? Do it. First you. Hey, did you get the answer -5? Of course you did. Because there's nothing here that makes it undefined. There's no holes, asymptotes, jumps. It's just a parabola. Just plug in, and the function value is the limit value. That's the definition of continuity. You can just plug in, and it's done. It's when something's not continuous that you have to work at it. The limit as x approaches negative infinity, okay, that's left end, of x over x squared subtract 3. You know this. So when I look at the power terms, notice the bottom is more powerful. Whenever the bottom is more powerful, the end behavior is 0. The left end and the right end. Over. 2 more. 29 and 30. Here we go. So 29, the limit as x approaches infinity. And we have x, 3x subtract 5 over 3x plus 2. So this describes the right end. There's nothing that's removable. So let's go. The power term on top, if I multiply it through, is 3x squared. On the bottom is 3x. Notice that it simplifies. The 3 simplify. And x squared over x. This is just x. So what's the right end behavior for x? X is a line with a positive slope. So where's the right end going? And the answer is infinity. You could also say the answer here does not exist. Both would be correct. Last question. Number 30. And you're done this assignment. I think you should try it first. The limit as x approaches 0, x over 3x plus 2. So this is not a question to do with end behavior because it's approaching 0. Step 1 is to substitute in, and that would give me the answer 0. And that's right. So notice it's not indeterminate. And 0 divided by 2 is 0. 0 on top, good. 0 on the bottom, bad. You did it. I am so proud of you. So you finish your assignment. Mr. G Math over and out. Until next time.